the big word. Sure, they would be Chinese. Okay, so it's a big pleasure to introduce Nicolas Brunel. Nicolas Brunel belongs to this department a lot. He has been here working with Daniel now many years ago, but and it was an important period. Then eventually Nicolas moved to States, he's in his years now. He has spent with us a period of a few months. It's a pleasure for him here to be with us for an hour today. And with his recent work is done, and so I thank you very much for this.
Well, thank you. Thank you, Anzo. So first, I'd like to thank a few people. I'd like to thank Giorgio for giving me the possibility of visiting his office, Enzo for his hospitality and his help, and also Federico for asking me to give a presentation here. I have amazing memories of my time here, like back in the 90s when, as Enzo mentioned, I worked with Dani Amit, first did part of my PhD here and then stayed for a postdoc. And it was really an amazing time. So I'm really happy to be back for a few months. All right, so this talk will be about a recent work that started so while after I moved to Duke. So this is the Duke campus, by the way. And by the way, you're all welcome to come and visit. It's a beautiful campus, a very green area, as you can see from this picture. And after a few months, there were a couple of other people came from France, but just for a short visit. And I think some of you know these people, Lenka Zdeborova and Florent Kanzakala. And we started to talk about potential inference problems in neuroscience, and we came up with this particular problem that I will tell you about.
We do the screen sharing because the image is not so good.
Okay.
So we prefer to do screen sharing.
Okay. All right, so what I'll do is I'll start with a kind of broad introduction to motivate the problem. So why are you interested in this particular problem? And then I will tell you about what we did, so the work that we did. All right, so one of the most fundamental hypotheses in neuroscience is that information is stored in brains through modifications of synaptic connectivity. So I'm just here starting with a cartoon to illustrate how that works. So the idea is that we have here shown a network of neurons in some brain structure. And the idea is that when you have external stimuli, for example, let's say visual stimuli, you see a novel, let's say you see a novel face or some novel stimulus that you've never seen before, that activates a group of neurons in your brain. So these red neurons in this case. And then the idea is that this activity in turn changes the synaptic connectivity. And here what's illustrated is the basic, a very simple mechanism that was hypothesized by Donald Hebb in the 1940s. Hebb was a psychologist, so he was, so people had no idea at that time whether the phenomenon of synaptic plasticity existed or not, but he hypothesized that if neurons are active together, then this must lead to modifications, particularly the strength of synapses must increase. So that's the often referred to as neurons that fire together, wire together. And so you can see that the nice thing is that after the stimulus has disappeared, long time after the stimulus has disappeared, so the neuronal activity came back to baseline, where there is now a trace of this stimulus now in the connectivity matrix. So that's this trace that maintains the memory of that stimulus. And of course, you can also store more than one stimulus in a network. This is another stimulus that's again stored. And so you can think about the connectivity matrix as a superposition of traces that are left by external stimuli that have modified this network. Okay. And there are, so this picture has been implemented in many different models, and in particular there are two broad classes of models where this picture has been implemented. One picture is that you have a synaptic plasticity process that leads to a structured connectivity that's highly symmetric, and particularly the Hopfield model is the prototypical example. I'll come back to this model later. And that can lead, it has been shown since Hopfield and many studies later that it can lead to attractor dynamics. So the network now has several fixed point attractors. Each of the fixed points, stable fixed points of the network is, you can think about it as an internal representation of one of the stored stimuli. But there are other scenarios that have been put forward. So if now you have more asymmetric connectivity, and in particular, if you have some temporal asymmetry in the plasticity rule, so if you have groups of neurons that are activated sequentially, and then the plasticity rule tends to strengthen preferentially synapses that are in the causal direction. So when the presynaptic neuron is active before the postsynaptic direction, then before the postsynaptic neuron, then you strengthen this synapse, but you weaken synapses in the other direction. So this leads to strongly asymmetric connectivity, and then this leads to different types of dynamics. In particular, now you can store sequences of activity in these networks. All right, but so what do we actually know about synaptic connectivity in real neural circuits? And by the way, interrupt me. Feel free to interrupt me at any time. So the traditional approach for studying synaptic connectivity is to use tools from electrophysiology. So, and the classic way is that you cut brain slices, then you can put the slice under a microscope, and now you can see neurons in this way. So you see there are many neurons here. And just to give you an idea, if you take a cube of 100 micron of size 100 microns, you would typically find about 100 neurons in that cube. And then here, so there are these 4 neurons, and this is an experiment where they recorded these 4 different neurons using these micropipettes. So this is really very challenging to do. And then what you can do is you can trigger activity in one neuron, let's say 1, and you check whether there is a connection by checking the response of the other neurons. And you can check all the possible connections. In this particular case, you see that only neurons 1 and 3 are connected. It turns out they are connected in both directions, but you can also have unidirectional connections. And in this way, you can measure really some very basic statistics of the connectivity matrix, right? You can measure the connection probability. So in cerebral cortex, in particular, it's known from many studies that it's of order 10% for neurons that are nearby. You can also measure things like motifs. So what is the probability, for example, to have bidirectionally connected pairs of neurons? And you can compare this to Erdos-Renyi networks, for instance. So there is this whole literature trying to find deviations from Erdos-Renyi in these kind of networks. And you tend to find overrepresentations of so-called clustered motifs when you have groups of neurons that are connected more than you would expect by chance. And that people mean by chance is basically Erdos-Renyi.
Excuse me, I have one question.
Yes.
Here, there is, I guess, a time resolution for the measurement, right? So you say that the neurons are connected when they are found to fire within a certain time interval, something like this.
No. So it's not, okay, yeah, good question. Maybe I should explain better the experiment. So here, the slice is silent. There is no activity.
Okay.
What you can do is you can trigger activity in a group of neurons, let's say neuron 1, by injecting a current. So you know that only this neuron fires in the slice. So now you're sure that this response in neuron 3, so you're injecting current in neuron 1, you're recording in neuron 3, and, well, you're sure that this came from neuron 1. Okay.
Yeah, but there could be an indirect fact, right?
No, yeah, okay, yeah.
So that's why I asked the time resolution. So
yeah.
the principle, one can fire before.
Yeah. Except that a single action potential in cortex can never fire a postsynaptic neuron that's at rest. This has been shown. This is basically, there is zero probability essentially. Or people have never found connections between this type of neurons that would allow a neuron to fire after just one. You need many of them to fire. But yeah, thanks for asking this question. So here, people are fairly sure, unless there is something that we don't know about, but that this is due to the firing of neuron 1. Of course, I think what you're referring to is that if you are recording a network in vivo, and so you have many cells that are firing together, and then people have tried to infer connectivity from these measurements, which are highly indirect, because then you try to infer connectivity from correlations. I won't be talking at all about this kind of. This is another interesting inference problem, and I think some people here actually worked on it. But here, this is like more like ground truth data. We know that there is this connection, and so. All right, but of course, you see that the drawback here is that, I mean, each of these neurons is connected to maybe thousands of other neurons, and you're just looking. So it's like you'd like to have access to a 10,000 by 10,000 matrix, and you're just observing just a 4 by 4 submatrix. So it's a very tiny fraction of the connectivity matrix that you're observing. Okay. Now, with technological progress in neuroscience, now in the last 2 decades, there is a new field that has emerged that is called the Connectomics. And basically, Connectomics, the idea is that you want to reconstruct the whole wiring diagram of, I mean, ideally the whole brain, or maybe a little bit less ambitious, just specific neural structures. And the idea is that you have all neurons in that structure, you want to know the whole connectivity matrix. Okay? And of course, that's like much more challenging. And in fact, this word is used at 2 different scales. Some people use it at the macroscopic scale, where people use techniques like diffusion tensor imaging, or you can also use viral tracing methods that you inject a virus in an area and then it propagates to structures that are connected to that area. And that gives you a picture at the macroscopic scale of the connectivity, how different brain structures are connected together. But of course, this is not something, this does not give you information at the single neuron level. This is something more macroscopic. All right, so here I'm interested more at the microscopic scale. And at the microscopic scale, the only way to get full information on a connectivity matrix is to use electron microscopy, because that's the only technique that gives you the right resolution to identify single synaptic connections with good accuracy. And then the idea, so I will show how that looks like. So you get electron microscopy images at very high resolution. Then the challenge becomes to identify different pieces of neuropils, so somas, axon, dendrites, and then you need to. So for each image, you need to identify what's in there, and then you have this alignment process that you need to align different sections. So that's really a very challenging endeavor. And until the end of the last century, people could only reconstruct extremely simplified nervous systems, and I'll give you the example of the worm called C. elegans that some of you might have learned about. But that changed about 20 years ago, where people introduced these more automatic data collection methods, where you use, in particular, this is called serial block phase scanning electron microscopy. So the idea is that you have this little cube, this volume of neural tissue that you have to fixate it, embed it, stain it. So there's this whole kind of new processing that you have to do it, which I don't have time to explain. And then you basically have this block under your electron microscope, and then you take a picture, and then you have this diamond knife that cuts a very thin slice of like something like tens of nanometers, and then you push up the little block, and then you go on and you take all these pictures, and you take a very large number of pictures, of course, if you want to reconstruct a volume of reasonable size. And so that's what it looks like, these kind of pictures, you see. So this is like 1 micron here. And here, this is very hard for non-experts to say what these things are, right? Maybe you have here, this is a piece of axon, maybe this is a soma, maybe this is a piece of dendrite, maybe this is an astrocyte. This is like super difficult to determine what these things are. But of course, experts can do it, and increasingly people are trying to find good machine learning methods that actually learn to do it, because of the sheer amount of data that you have to process. So this is just to give you an idea. This is a little cube of maybe 10 micron side, and well, you can see that from what you can see is that this is a piece of dendrite that's embedded in this tissue. You see that there are these little spines that are protruding. Spines are actually the sites of synaptic communication, if you know. So this means that this particular neuron, this dendrite, has basically a few synapses that are at each of these spines. And you have to reconstruct this 3D volume just from these sections, where this is one section in XY plane, and this is this particular dendrite, and this is a YZ plane, and you have this color dendrite. So this is really a very, very hard problem, and even for this very small volume of 10 micron cube. Okay, so a brief timeline, just to tell you the progress that's been done in the past 40 years or so. So 86 is the publication of the first connectome of the first published connectome, and that's this worm C. elegans that has 302 neurons exactly. And that's from the group of Sidney Brenner, so who pioneered the study of C. elegans. It took 15 years of work to reconstruct that particular connectome, okay? Because everything was manual at this time. You didn't have all these tools, that automated tools to help you. This is still nowadays the only organism with the fully reconstructed connectome, but I will show you some progress. And actually, until recently, there was only one connectome, only one worm had been reconstructed. So we didn't even know about the variability from animal to animal. But that changed a few months ago, where a group published 2 connectomes.
How variable they are?
It's actually quite so. Unsurprisingly, there is both kind of a relatively fixed component, but there is also variability around it. So in fact, I didn't have time to really read that paper in detail, but as you would perhaps expect, there is some kind of there are connections that are present in both, and then there is some variability around it. So. And what's nice with this particular case is that you can actually visualize the connectivity matrix, right? 300 by 300, you can still plot it and see the individual connections. So that's really nice. And in particular, here you see that you can divide neurons in C. elegans in 3 groups of approximately the same size, where you have the sensory neurons, which are all the neurons that are activated by external variables like touch, specific odors or chemicals. So these are the sensory neurons. They are about 100. And then on the other side, you have the motor neurons, so neurons that are connected to muscles, so neurons that cause movement. And in between, everything else is called interneuron in this case. And these are neurons that are in between, basically. And you see that you have this connectivity matrix, and you see that it's already not, I mean, if it was a simple feed-forward structure, like sensory neurons projecting to interneurons, motor neurons, you would have only connections in these 2 blocks, right? But you see that there are lots of connections also, like recurrent connections between sensory neurons, between interneurons, lots of them, and also even within motor neurons. So you see already that even in these simple animals, you have a lot of recurrent connectivity, potentially leading to interesting dynamics. And you have also connections which are the other way, so called sometimes top-down connections. And that's, of course, a feature that you see in all animals. Well, of course, that in most animals, like mammalians, the vast majority of neurons are in between sensory and motor, of course. All right. Then, as I already said, so in 2004, there was this major breakthrough, which is this serial block phase scanning EM technique, and that dramatically sped up the data collection process. But at that time, you still needed humans to actually read those images. So you still had this bottleneck. But still, that led to multiple reconstructions. So that led kind of a renaissance of that field, which was kind of more or less dormant because it had been such huge amount of work to reconstruct just this tiny nervous system that people just gave up afterwards, right? And then you had reconstruction that came out, so 300 micron cube, mouse hippocampus, the whole mouse retina, actually, that's, well, actually not the whole, but a big part of it. And then mouse cortex, this is like 50 micron per cube of cortex. Unfortunately, this is still very small. I mean, what you would like are reconstructions in which you have cells that are reconstructed untitled. In particular, you can reconstruct, for example, maybe the whole connectivity matrix of neurons that are sufficiently far from the border. But the extent of neurons in mouse cortex are several hundred microns up to millimeters. So you're still reconstructing only a small part of the neurons that are in that volume. And so that basically doesn't tell you much about the connectivity matrix. Okay, last year, a big advance. And now this is really a major enterprise with something of order of 100 people working on this. So they published a heavy brain of a Drosophila. Okay, that's the next animal. And there is a whole team at Janiga Farms, which is this HHMI institute in Virginia called the FLY-EM team. And they collaborate with Google has also a whole team working on connectomics and developing new machine learning tools. And so that helped dramatically, but still need 50% year of proofreading the EM data. So even with the help of machine learning tools. So it's still not fully automated. Just to give you an idea, so this brain is contained in a cube of 250 micron side, and then the EM images are at 8 nanometer resolution. So this is really a very high resolution. And so just to give you an idea, this is like tens of terabytes of data. So this is like 26 teravoxels of data. This is a huge amount of data just for this tiny fly brain and a half fly brain. And in this volume, you have about 20,000 neurons, what they call uncropped neurons. There are about 100,000 neurons in the whole brain of a fly, and the uncropped neurons in the heavy brain is 20,000. And now you have about 20 million synapses already in the tiny fly brain. So you have already something like 10,000 synapses per neurons, while in worms you have only about 20 synapses per neuron. So fly brains are way more complicated than worms. Okay, so what's next? So we're expecting next year the full fly brain. And of course, then in terms of mammals, which would be great to have information about mammals, well, there's a kind of, one of the holy grails of the field is to get this access to this cubic millimeter, which then is really the size of local networks in cortex, where basically you would have, for neurons that would be sufficiently far from borders, you would get most of their connections and most of their dendritic and axonal arborizations. So you would get really, but this is still probably several years, because basically you see that we still have, the volume would or be 2 orders of magnitude larger than the fly. Okay. Well, so now the next question, of course, the one question is how to measure these connectors. But then once you have these big matrices, what do you do with them, right? What do you learn with them? So people do these things like, for example, all these kind of network characterizations, motif probabilities. Is it like small world? Is it scale-free? All these things. One question that we asked, what we wondered is whether. So of course there is this hypothesis that connectivity matrices store our memories. Our memories are stored in our matrices. So this was popularized by this guy Sebastian Sung that gave a TED talk. So if you want to watch it, that was entitled "We Are Our Connectors." And so. Suppose that I give you this big matrix, can we actually infer the information that's stored in it? And as I already said, it turns out that in about a couple of years ago, so Florent and Lenka came to Duke. They were invited by the math department to spend a semester, and they came with Sebastian, who was a postdoc. And so talking about inference problems, we decided to work on this particular problem. Okay. Any questions at this point? No. All right. So we started with a very simple problem, and so the question is whether the idea is that there is a plethora of models, of network models where the connectivity contains information about basically different patterns that are stored, and the simplest one is the Hopfield model that probably many of you know about. And so in the Hopfield model, this was from '82. So what Hopfield introduced is a model in which you have, so the goal of the network is to store a number of random IID binary pattern psi I mu, and they are, in this case, they are just plus or minus 1 and unbiased. So the probability of being active or inactive is 50%, and there are p such patterns. And by storing, he meant that these patterns should be fixed points, attractors of the dynamics. They should be stable states of the dynamics of the network. And he just proposed this very simple connectivity matrix. So, and I here Jij, H should be for Hopfield, where you just take a linear superposition of the products of the pre and the postsynaptic activity. So psi G mu would be the activity of the presynaptic neuron, psi I mu activity of the postsynaptic neuron in pattern mu. Mu is the index of the patterns. And you just kind of have this linear superposition in the connectivity matrix. And he found using simulations that, yes, it works, provided the number of patterns is smaller than some value that scales with linearly with n, with some prefactor alpha c, which is about 0.14. And this was actually computed using statistical mechanics techniques, so the replica method by Amit Guthrod and Sompolinsky just a few years later. So that was a very nice application of statistical physics of disordered systems. Yes?
Here the connectivity is fully connected.
Yeah, that's actually my next point. So that's clearly not a good model for for real brain networks. So that thanks for anticipating the my next bullet point. Of course, yeah. So as you say, this is unrealistic, and actually kind of two key features of the network that are this network that are unrealistic. So it is fully connected, and real networks have typically connection probabilities of, I mean, it's depends on distance, but typically it's about 10% for neurons that are nearby. Another thing that happens with real synapses is that they are sign constrained. Some synapses are excitatory, they are basically non-negative. Others are inhibitory, so they will be non-positive, right? And many models have, in fact, hypothesized that the memories are actually stored in the excitatory connectivity matrix, and for reasons that are a bit too long to explain. But here we take the assumption that all synapses are excitatory. And that means that, of course, you need to include also inhibitory neurons to stabilize activity, but I won't really talk about that here. So we introduced this like a simple model that adds these two constraints, and we can call it a rectified Hopfield model. The idea is that we are taking the Hopfield model, we have a threshold here, tau. We can also use some noise. We can add some noise because we're expecting everything in the brain is very noisy. So here we go. There is a zeta ij, this noise, and then we rectify it. Phi is this basically something that's now known as ReLU function, so rectified linear function. And you see that basically, so you have two parameters now, two additional parameters in our model. So you have the variance of this noise, and then you have tau that controls the connection probability, the higher tau. So you can basically, if you want to have a specific connection probability, you can choose the threshold that gives you the.
Voilà.
Yes.
In this way, you are cleaning all the negative couples. So in some sense, you have no inhibitory.
That's right. Yeah. So yeah, exactly. So in fact, so. What you have to do then is you have to add inhibition. You can add unstructured inhibition, which you can think about it as an activity-dependent threshold in the dynamics of neurons. So you can do that. So people have done that, and that kind of then works also. So you can keep more or less the same properties of the Hopfield model by doing this separation between excitatory and inhibitory neurons with information encoded only in the excitatory. To excitatory matrix. Yeah, and by the way, this is related actually to a class of models that Chaim Sompolinsky studied also in the 80s. So he didn't study this specific case, but he studied cases, for example, where this is actually a heaviside function. So you have clipped synaptic weights. He studied the case where also the case of random symmetric noise added to it. So that's one particular case of a whole family of models that is studied.
What is the biological justification to have zeta symmetric as well, so that you have?
Yeah, very good point. In fact, there is no biological justification, and this is just because of the kind of techniques that I will introduce later that unfortunately can be used when the connectivity matrix is symmetric. Real connectivity matrices are never fully symmetric, though they tend to have a degree of symmetry that is actually, you can think about it as being intermediate between random asymmetric and fully symmetric. So if you take the correlation coefficient between Jij and Jji in cortex, would be typically about 0.4, 0.5. So it's not fully symmetric, but it's not either completely random asymmetric. All right, so we have this. Okay, so that's kind of the statement of the problem, basically. So we have this model. So we take the Hopfield matrix. We have now we add noise, we rectify it. So we can, of course, easily compute the conditional distribution. So we have a distribution. Okay, so this is this should be removed here. I just rewrote an equation that I forgot to drop this equals 0. So this is the full conditional distribution of Jij given the Hopfield matrix. So there is a delta function at 0 because of the threshold, and then this is the part at positive weight. So this is a rectified Gaussian, basically, the distribution of weights. And now the question, can we actually, so suppose that we are given this matrix, can we infer the size? And in fact, when P is of order 1, so in the case when P is of order 1, this is actually similar to so there is a broad range of problems that are basically called low-rank matrix estimation problems. So you suppose that you have some low-rank matrix, and then there is noise, or it's sparse, or so there are many different variants. And then the question: can you estimate basically can you estimate the low-rank part of that matrix? So that's very similar to discuss a problem. And in fact, Lenka and Florent, when they came to Duke, they had already worked a lot on this type of problem. So they had already tools that they can readily apply to this particular problem. So that was nice. So what are these tools? So briefly, okay. So to start with, we'll assume that we know some of the hyperparameters of the problem. So we have these parameters nu and tau. And of course, we have also the distribution of patterns, which is in the Hopfield model, it's given. But of course, we'll see later that that's not very realistic also, these particular distributions, but we can also generalize to, for example, we can have bias patterns. Okay, so to make it simpler, we can start with the case when we know these hyperparameters. Then we can take a Bayesian approach. So we have a prior distribution on the patterns, which is here, and we can use Bayes' rule, and we can compute basically what's the posterior distribution of the pattern. So psi here is this big matrix, P by N matrix containing all the patterns. And so what's this conditional distribution P of psi given J? And so you have basically this. This is the P of J given JH, which is a function of the size, and then this is the prior, and this is this normalization factor. And now basically we could say, okay, now it's easy. We can just take the marginals of this. So for each particular psi I mu, I can take what is the I can compute the marginal by integrating out all the other variables. Well, it turns out that basically, of course, in n dimensions, when n is high, well, it's basically an intractable problem. Marginals, as probably many of you know very well. But there have been people have introduced techniques to still to address this question. In particular, the approach here is to use this method called approximate message passing. And in particular, in the case of low-rank estimation, there is this approximate message passing algorithms. In this specific case has been termed the low ramp. And in particular, there is a very nice kind of review paper about it by Le Sueur, Kurzakala, and Steborova in 2017. And so with the relationship with kind of statistical physics problem is that this algorithm turns out to have a form that's analogous to the TAP equations in disordered systems. And the idea is that this is an iterative algorithm that will produce estimates of the means and variances of these pattern size. So just to give you a brief sketch of how that works. So first, approximate message passing. So this is initially you start with a belief propagation algorithm. And that belief propagation algorithm is the drawback of this algorithm is basically you have to compute these messages from a source node to a target node, and this is basically you have an algorithm that's involved of order n square variables, and so what people have realized, like Andrea Montanari and others, is that you can actually reduce that to an approximate algorithm that has only of order n variables, and so that involves some approximations. And eventually, what you get is that in this algorithm, what enters, so the information about the weights that enters is basically this something called the Fischer score matrix. So the Fischer score matrix is the derivative of the log likelihood, basically the logarithm of the conditional probability of Jij given a particular Hopfield weight, which here I call W for simplicity. And in this model, it's very easy to compute. So you have these simple equations. And so this score matrix tells us basically the information that the Jij gives about the patterns. Okay, and then you kind of apply this machinery that was developed by many people. So you have to introduce parameters. So there is a vector of parameters for each neuron bi, where this is a vector because there are p patterns. So this is a p-dimensional vector, and you have also a matrix AI. And they are given by these equations. So they are given by these equations, where so in these equations, so S is this score matrix. This hat psi is the estimator of patterns. The hat here means that the current estimate of the patterns, right?
Is an estimate or an estimate?
An estimate or an estimator. That's actually the mean. Okay, maybe I can. Okay, so it's an estimate of the mean of the particular psi, and you have also an estimate of the variances of the distribution of the psi's that you're computing, that are given by these A's and B's. So basically, you have this function here, f of A and B, and here you can think about it as, so this is you can see that this is the estimate of the mean of psi. You have the psi here. P of psi is this prior. And this exponential here gives us basically the information that you have from the matrix J. And basically, you iterate these equations until convergence. So that's the idea of these algorithms.
Do you imagine theorem about the convergence of the algorithm, or?
Yeah, okay, so good question. So that's, I mean, I wish I knew more about these things. And so I think in some cases, it has been proved to converge. So there is a whole, in fact, I think this is a field where there is a lot of activity nowadays at the intersection between statistical and physics and math, or statistics, and where people are deriving rigorous, like mathematicians or statisticians are deriving rigorous methods, rigorous proofs using the insights provided by statistical physics. But that's not really a field where I'm an expert, so I can't really tell you. Maybe some other people in the audience know more about the status of like in which problems exactly to get rigorous proofs or not. Okay. So basically, this is an algorithm that you can use for any n. As you can see here, you just need this. What you just need is this score matrix here. Now, of course, we'd like to study the behavior of the algorithm, the typical behavior of these algorithms in the large n limit. And you can use something that's called the state evolution technique. And that's actually basically nothing else as what physicists call the cavity method, essentially. And the idea is that what you would like to compute is the mean squared error of the reconstruction of the. So you have a reconstruction psi I hat psi, and then you have the true pattern psi I. And at any given time, you'd like to compute basically this reconstruction error. Then you can express this mean squared error as a function of a matrix of overlaps between the reconstructed patterns and the true patterns. And this is a whole matrix. This is a whole P by P matrix in general. And in fact, what this state evolution technique, basically what it allows to do is from the from the approximate message passing equations, you can derive the so-called state evolution equation that basically gives you the dynamics of these overlaps. Where this you recognize again this function fin that I wrote down. Here you have a double average over psi is basically an average over the prior distribution of the psi's, and W is some p-dimensional vector of Gaussian random variables.
So excuse me, just to understand this, you can do this check when you generate the data with a synthetic model where you know what is
So
it's just to test the algorithm.
Yeah. So that's what I will show later. Yeah, I just want to explain the method, but of course, that's clearly the next step is to check whether that works. Yeah, just some last equations, and then I will show some results. So basically, what I want to point out is that you have a parameter here, delta, that enters this equation, and you see that basically everything. Well, the nice thing about these equations is that everything about all the parameters of the model are basically contained in this parameter delta, which is a kind of effective noise. And it turns out that the effective noise, so it's the inverse of the effective noise is nothing else but the variance of the score, so the score matrix. And in statistics parlance, this is nothing else that's the Fischer information. Okay. And so the equation for this particular model is given by this. You can write it down. It's a relatively simple equation where you have these two parameters. Tau is the threshold, and mu is the variance of the noise. Okay. All right. So let's start with the case of a single pattern. And does it work if we have a single pattern? So for a single pattern, basically all the previous equations involve vectors and matrices, that is p-dimensional or vectors or p by p. So here basically ends up with a single variable. So everything simplifies drastically. And in particular, state evolution is given by this really simple equation. And you can see, it's very easy to see from that equation that basically the reconstruction will be possible if delta is smaller than some critical value that's just equal to 1. It's just the slope of this function of m of t at 0. And basically, so you can check that everything works as it should. So you can basically plot these. So the mean square error. Basically, you can plot it as a function of this parameter delta. So when delta equals 0, when in the noiseless case, basically you can actually fully reconstruct the patterns. So the mean square error is equal to 0. But when the noise increases, then of course it becomes harder and harder. And at some point here, at 1, you do no better than a random guess when delta is larger than 1.
Is the prior on
the prior is I'm still at this unbiased prior where so equal probability of +1s and -1s.
From this picture, the error will seem to be below 1. So it's probably at this point with very large error, yes, but please understand, left.
Yeah. So I haven't finished explaining I should explain what the different curves are, basically. So these full curves here are basically the state evolution. So basically it's essentially solving this simple equation. And you can do it in two different initializations of m. You could start with m close to 0 or m close to 1. So this is called the random and informed cases. And this will matter later on because then the two curves will not overlap when you have multiple solutions for these equations. And you see that basically there is a nice smooth curve by just solving this equation. So the fixed points are when they reach the fixed point. And then these are simulations using this approximate message passing algorithm. And it tells you that, well, so there is a point here where maybe it's not exactly, so here we are not exactly at 1, and it seems that there is a small departure from there. But otherwise, it seems to work pretty well. So it's instructive to look at what happens in the plane of these two original parameters. So now, as I told you, everything depends only on delta, this effective noise. But so now if you plot as a function of tau and nu, so tau is this threshold and nu is the noise variance. Well, this is the region where reconstruction is possible in this blue region. So this is a region where delta is smaller than delta c. So this is the line where delta is equal to 1. Note that it's also instructive to look at what are the connection probabilities on this plane, okay? And it's easy to see that the connection probabilities only depend on the ratio between mu and tau. In particular, tau equals 0, of course, the connection probability has to be 50%. So that would be the line here. And of course, as you increase tau, you will decrease the connection probability. And again, I just remind you that typical connection probabilities, in particular in cortex, would be about 10%. What's interesting, though, is that if you look at a given tau, and you increase mu, what you see is that when mu is really small, then it's actually, you cannot reconstruct the patterns. And the reason for that, so I should come back to the, which seems surprising, so it looks like there is a minimal amount of noise at which you are able to reconstruct the patterns. And the reason for this is coming back to the model. Well, we have just one pattern here, so this is actually either 1 over, this is actually plus or minus 1 over square root of n. So if tau is positive, in the absence of noise, all the connections are at 0. So of course, you can't reconstruct anything. On the other hand, if you add noise now, then you will start having some weights that will be now positive. So you get some information. And of course, the weights that are positive are biased towards, they are more likely to be positive is jh is equal to plus 1 over square root of n. So that's why basically you get this particular curve. So you need a minimal amount of noise so that you can actually reconstruct. But that's basically because otherwise your network is just too sparse. You don't have enough weights.
In this picture, you can tell us what is the trivial line. So suppose that I want to reconstruct just looking at the positive couplings, which I know are correct. So since the nonlinear function is a random function.
Yeah.
If I just look at the positive couplings, these are given by the Hopfield rule.
Yes.
So in principle, I could solve the equation J is equal to the scalar product of psi I psi j only on the positive couplings. Is a let me say is a naive inference.
But you have only a fraction of those weights that you can access.
That's fraction.
Yeah. Right.
So once the fraction is non-zero,
yeah,
instead of running approximate message passing, I can just solve this equation. It's a quadratic equation.
Well, but I think okay. So
the question is whether you know what is the region where it works. Just to convince that approximate message passing is doing better than just solving naively psi dot psi j is equal to jj on all the jj that we know that are correct.
Sure. Yeah. That's a good. Well, it's not psi I equal psi j. I mean, this is more like a inequality that you have to solve, basically. Well,
because there is more noise, so I was focusing in the close to the x-axis where nu is small. So what is the minimal amount of noise? Because that is the minimal amount of noise that the approximate message passing needs in order to work. But
well,
is that really optimal?
I'm pretty sure that it is in this particular case. I wouldn't be able to prove it, but I mean, from
maybe because it's a dense problem, but since you cut off with a nonlinear function part of the couplings, I would be curious to understand whether the remaining couplings are still providing.
Yeah, I don't see. I mean, yeah, I have to think about it, but.
Because this, in some sense, is giving information whether how much is important to consider also your knowledge on the zero couplings. One way, so in the naive approach,
right. I mean, you
disregard the zero couplings. You say, I just solved the equation for the non-zero couplings. In this bias optimal approach, obviously, you put into the game also your information, your prior information on the probability of having a zero coupling. This is the information we are adding. So my question is whether that information is relevant or not, since it relies strongly on the on the prior of the parameters that is usually unknown. So all these bias optimal settings obviously is unrealistic for practical applications. So
so I think the question is whether we use alternate methods. There are many other methods that we can use. There are spectral methods. You can use PCA, for instance, like the simplest possible method. I think the belief in the field that I think is that this would perform, I mean, approximate message pathing would perform at least as well as those other methods. Yeah. But I can't prove it to you, I have to say. And maybe, I don't know, Lenka and Florent have stronger arguments. But I don't. But yeah, that's a good question. Whether and we didn't try other methods in particular case. I'll come back to that in the discussion. Okay. Okay, it turns out that in the case where you have a finite number of patterns, but they are just not one, it turns out that basically the state evolution equations basically also simplify, and basically this matrix of overlaps become diagonal, and this should be a M, sorry for the misprint, this should be a MT, and this is actually, you end up with exactly the same equation as in the case M, as in the case when P equals 1. So that's very simple. And I'll come back quickly at the end of the case where you have a very large number of patterns where things start to break down. So just a quick, by the way, I'm not sure, just let me know, because I know that I've started pretty late, but I don't know if I should stop now.
Until at least 10 minutes.
Okay, good to know, okay. Okay, so we also consider the variant of the Hopfield model, and the motivation is that there is another unrealistic feature in the Hopfield model is that it assumes unbiased patterns, which means that essentially half of the neurons should be active in any stored pattern. That's highly unrealistic. We know that in biological networks, the neuronal activity tends to be sparse. At any given point in time, there is only a small fraction of neurons that are active. And so how does that affect these results? So in particular, we can use a generalization of the Hopfield model that was introduced by Misha Tsodix and Lev Feigelman in '88, where basically you use a simple generalization where now the probability to be active is now a parameter rho, and rho can be anything you like from 0 to 1, and the relevant limit would be the rho going to 0 limit, in fact, or at least rho being small, maybe of over a few percent. There are estimates in various neural circuits that typically give estimates of over a few percent, maybe. And so you have some probability to be active, which is rho, and of course, probability to be inactive to be equal to 1 minus rho. And interestingly, so you can generalize the calculation to this case, basically it just consists in changing this prior. And interestingly, what happens is that for small enough rho, so when the coding is fast enough, and there is this critical value 0.2113, where now when you solve these state evolution equations, you find that now you get a first order phase transition. And in particular, now it depends when you solve these equations. It depends whether if you start from a random configuration, so m close to 0, you see that again when you're above delta equal 1, you get well, it's actually delta c now is different from 1, so delta c will depend on rho. So you see that basically you have you cannot reconstruct the patterns. If you start from an informed initial condition that is m close to 1, then you can actually get some information about the patterns. And this is typically, so when this when this behavior arises in these inference problems, so typically that signals a so-called hard phase. So this is a phase where it becomes very hard to reconstruct the patterns. And in fact, that's what you see when you simulate the message passing algorithm starting from a random initial condition. So you see that in this case, you typically don't reconstruct the patterns. And this kind of hard phase become larger and larger as rho decreases. Okay, just quickly, what about now if we increase the number of patterns? Well, things, as you would expect, things become worse progressively. So we can still use this approximate message passing. we see that you see here 10 patterns, 20 patterns instead of 1. These are for networks of 2,000 neurons. So we are still actually at p that is still very small compared to n. And this happens both in the case of the Hopfield. Well, actually, this is not a good name. This should be Hopfield prior, and this is Sodix prior. This is also binary in Sodix case.
Hopfield is
no, Hopfield is binary, but unbiased. So that's the. Okay, and we try to investigate numerically what will be the scaling of the critical number of stored patterns that we can get. So what we can do is we can increase p for a given n, and then we compute for different realizations, we compute the mean square error, and we see that when p is below some critical value of p, so this value is computed from it's the value of p for which more than half of the realizations will give to good reconstructions, and so on that side more than half good reconstructions, and on that side it's the opposite. And then we can see how this critical p varies as a function of n, and you get something that looks like a power law, though of course we can't be really sure that it is really a power law, given we can't really go to really large sizes. So in particular, in the Hopfield case, we see that this is the blue curve. This is something like 0.6, but plus or minus something here, which one should compute. And then in the Sodix case, this is the orange curve. And we have another scenario that we studied, which is, well, actually, Sodix case, the skewed case here. That's the green one. I mean, in all these different cases, we see that. Anyway, this would be a sublinear, so the maximum number of patterns that we can store varies sublinearly with n. Okay, so to conclude, we have derived conditions under which it's possible to reconstruct patterns stored in this simple model. And we see that when p is over 1, then it's possible, provided effective noise is not too large. And also, we have simulations indicating that this extends to p smaller than than n to some power gamma, where gamma is over 1/2. Okay, so let me now go to just a list of limitations of this work and potential future directions. So one obvious limitation here is that we have assumed knowledge of hyperparameters, and it's not obvious that of course, we do have some information about, for example, the average activity level in specific neural structures, but we don't have probably a very accurate information about this prior distribution of patterns. And also the noise. So something that we can quickly, that is easy to obtain is the connection probability. So we have some information about the connection probability. So that gives us some information about this parameter tau and zeta, but for example, the noise, the variance of the noise might be hard to estimate. So it's possible in some cases to extend. It's been shown in other problems that you can extend these algorithms to the case when you don't know the hyperparameters, using basically variance of the expectation minimization algorithm. So you start with some guesses of these hyperparameters, and then you iterate, and then you update these guesses, and you try to basically maximize your mean squared error. There are, as was mentioned by related to a point that Federico mentioned, you can imagine other methods to infer patterns, and spectral methods are an obvious alternative, in particular PCA. And it's of course, in fact, even easier to implement than AMP. One con is that typically these methods do not really incorporate prior information. Okay. One problem that was also mentioned: real connection matrices are not symmetric. So what one can do, if we have real data, one could first symmetrize the observed matrix and then apply these methods. But more generally, so here that one assumption here is that if we had a temporally symmetric Hebbian learning, then the part of the connectivity matrix that stores information about the memories would be symmetric, and then you could imagine that different synapses, the two different synapses have, of course, uncorrelated noises. There is no reason why the noise terms in the two synapses that are far away would be correlated. So that would give rise to the asymmetry in the connectivity matrix. So that's one scenario. But of course, another scenario is that there is also the asymmetry contains some information about the patterns, like in these models that store sequences. Then we need to generalize these methods in this case to non-symmetric matrices. And finally, there is a problem. So here, might seem a little bit disappointing that we can actually reconstruct a number of patterns that is very far from the storage capacity of the network. So these networks are able to store extensive number of patterns. But then in that case, when you're close to storage capacity, we actually cannot reconstruct them using these methods. And here, this is related to a problem of factorizing matrices with the extensive rank. And that's known to be a very hard problem. So yeah. So that I don't think there are currently methods that would allow us to do this. And that's this is the last slide. So thank you for your attention.
So, which is biologically really relevant? I mean, about your last comment. Biologically, the area problem would be to have a large number of patterns, or it depends from experimental context, or
right. Well, so one would expect that. So if networks in the brain are optimized, at least in part, for kind of maximizing the amount of information that you can store in these networks, you would expect that that they would be able to reach this extensive number of patterns. However, in these models, there is an assumption that all patterns are equivalent, and that's clearly not the case in real networks. And we know that our memories are not all equivalent. There is a big heterogeneity in different memories. So I think if we had a model, for example, where you have more heterogeneity, so patterns are embedded with different strength, and you have perhaps an extensive number of memories, but there is a whole distribution of strength of embedding, then perhaps these methods could allow to reconstruct the kind of more strongly embedded memories that kind of maybe you see or more embedded memories. So that's something also potentially interesting future direction that we have not been considered.
First one is about the sparsification, because the way you produce as parts, or not even sparse, but at least diluted, so we say you are not really changing the order, so they are still order n squared.
Yep.
Well, it depends on the value of tau, but they it's one way. But if I had to think in some sense, a model that takes into account that some neurons are not firing on some patterns. So the number of neurons that fire are a tiny fraction.
Yeah.
Why don't you use from the beginning pattern xi that takes plus, -1, and 0? So why you first build the coupling considering as if all the patterns involve all the neurons firing, and then you apply a nonlinear function? Seems rather unrealistic. So why don't you start from the beginning with sparse patterns?
Sure. Actually, exactly the model that you described, we also studied that model. I didn't show it because it was kind of, but that's actually the curve. The model you described is the sparse model, is the orange one. So exactly what you described. Yes, I mean, I agree with. So we just started from the simplest model. That's the short answer. But yes, we did also study exactly the model you studied.
In that case, you do not need a nonlinear function. You just really take the Hopfield rule, and most of the couplings will be 0. So in some sense, you get.
Wait. So you're really thinking about a really sparse limit then?
Yeah.
Yeah, so
the
right.
couplings is present only if
Well, so in fact,
neurons are non-zero probability of being both active on most of the
okay. So that's another part because there is a model there is a classic model in the literature called the Fischer model, where the connectivity matrix is basically a Heaviside function of some of the mu, value, where these are zeros and ones. Okay. So basically, there is a connection if in at least one panel the two neurons were active together. So that's really very nice and simple. In fact, it would be interesting to study also this case. The drawback, though, is that here for this model to have, so the capacity of this model is not extensive at all. Okay. And in fact, but however, you can show that if you take really sparse, so let's say we have this particle rho, which is the probability that psi mu equal 1. If rho is scales as log n over n, then this becomes close to optimal in the sense that the information stored in the network is about 1 bit per synapse. But for any other scaling, it's the information is vanishing really close to 0 in terms of bits per synapse. Well, yeah,
that's in this case, having the pattern would be non-trivial because there is a nonlinear function relating the coupling with the pattern.
Right. Yeah, that was just to see, there are many variants that have been studied in the literature. We just I see this more like at the beginning. But yeah.
Since we are on this picture, look here that just a small numerical comment.
Yeah.
The orange data look quite different from the blue data. I mean, I would not say looking at it like that.
Yeah.
First model is a clear, say, power law behavior. I mean, it depends on error, but if you look at that.
To be frank, I'm not very happy with that.
Yeah, I don't exactly clean it, but
no, I don't. But yeah, at some point we.
No, because it's very deep. Indeed, the binary is pretty clear, right? I mean, you have a fluctuation on one point, but the binary.
No, I think we should. I mean, you should certainly revisit.
Really, sparse model you should, because you could have a surprise.
Yeah, I agree. Yeah, the thing is that so we worked on this while they were at Duke, like for 6 months, maybe in 2018, and then after they left, like everybody starts doing other things, and so it was only a few months ago that we actually managed to put together. At some point, fatigue starts to.
Yes.
Okay, let's put this on an archive now because otherwise we never.
Sorry, fatigue.
No, it's about when you comment on the fact that you would like to infer also an extensive number of patterns. The question is whether this is information theoretically possible.
Yeah.
Can you prove that that is possible? So the information is there and it's hard to extract. What is the?
Yeah, that's a good question. I can certainly not prove. I don't know if it's possible to prove it. I don't know. This is really a big question mark for me. So.
When the extensivity, when the number of patterns is extended.
Yeah.
On some threshold, you have a spin glass, the original of so that case,
Right, but it's beyond the capacity, right?
Yeah.
So you might hope that if you're below capacity,
of course.
then maybe it's
I'm afraid that if you have a threshold, a transition before alpha.
Yes. Yeah.
The order of magnitude is fine. It's n square number that you want to infer, and you have n square numbers at your disposal, but that's not enough.
Exactly. Yeah. Yeah. Good question. I'd love to know the answer to that question.
More questions? From the net? No questions from the net.
Oh.
Then, okay, so again, thank you, Nicolas, very much.
No, okay.
It's very nice to have a presence seminar after so long.
Yeah.
After maybe 1 year ago.
Oh, really? Oh, wow.
Yeah, we did. Yeah, right.
Maybe INFN keeps doing seminars present.
Because for a long while, just repeat